Okay, this is Math 1090, Section 2.2, Solving Systems Using Matrices. Let's do the definitions. A matrix is a rectangular array of numbers arranged into rows and columns. So I have a couple of examples here. The first grid of numbers has 4 numbers in it. We call this a 2 by 2 matrix because it has 2 rows and 2 columns. Okay. The next matrix here has 3 rows and 3 columns. It's a 3 by 3 matrix. And the next matrix is special. It is a 1 by 3 matrix. And whenever one of the dimensions of your matrix is 1, we give that matrix a special name. We call it a vector. You can still call it a matrix, it's fine, but we typically call it a vector. And so this is a row vector. And then finally we have a 3 by 1 matrix. And since this has one of the dimensions is 1, this is a vector as well, but it's a column of numbers, so it's called a column vector. All right. The coefficient matrix is the array of coefficients from a linear system. So if you were given this linear system here, the 3x plus 4y equals 7 and the other equation, then the coefficient matrix would just be the coefficients of x and y put into a grid. And so we would get a 2 by 2 coefficient matrix here. An augmented matrix is created by adjoining the coefficient matrix with the right-hand side of the system of equations. So we take the coefficients from this side of the equations and we create a matrix from those coefficients, and then we take the constant values on the right-hand side of the equations and we create a column vector from those, and then we augment the coefficient matrix and the column vector together into a single matrix. This is a 2 by 3 matrix. And then we often put that little that line in there to just help us remember, you know, where that these are constants instead of coefficients. Okay. Elementary row operations, or we might just say row ops or row operations. So these are operations that can be performed on a matrix representation of a system of equations that don't change the solution to the corresponding system. Okay, now that's very important. There's 3 kinds of elementary row operations. Excuse me, and the key idea is that by performing any sequence of these, finite sequence of these elementary row operations, you will change the look of the matrix that represents your linear system, but the corresponding system of equations to that matrix, that augmented matrix, will have the exact same solution as the original linear system. Okay, so the key idea is that these row operations preserve the solution set for the system. Okay. Next definition, row-echelon form, or REF. So we say a matrix is in row-echelon form when there are ones down the main diagonal from the upper left corner to the lower right corner, and zeros in every position below the main diagonal. Some books use a slightly more technical definition, but this will suffice for this course. Okay, so we have row-echelon form, and next one is reduced row-echelon form. So a row-echelon form matrix is a matrix that is, first it has to be in row-echelon form, so it has to have ones down the diagonal and zeros below the diagonal. And then 2, the leading entry in each non-zero row is a 1. 3, each column containing a leading 1 has zeros everywhere else in that column. So to be in reduced row echelon form, what that really comes down to is you have to start with row echelon form, and then you use the 1s on the diagonal to clear out the elements above the diagonal, above the main diagonal, and so you have zeros above. And so when you're in reduced row echelon form, the leading 1 of that row is the only element in its column. So for example, here, this first 2x2 matrix, the leading 1 for the first row is this element right here, and notice that it is the only non-zero element in its column. Okay, and then similarly, this one right here is the leading row, or sorry, the leading element or entry for the second row, and notice it is the only non-zero element or entry in that column. So this matrix is in reduced row echelon form. Okay, what about this one? The leading 1 for row 1 is there, and everything in its column is 0. So far, so good. And then the next leading 1 in row 2 is this one right here. And notice there's a 0 above and below. Okay. Now, notice the third row doesn't even have a leading 1, so there's nothing left to check. Okay. So notice this, in this entry right here, this is a 1, but it's not a leading 1. When we talk about leading entries, we're talking about the first non-zero entry for a row. We're going to be always talking about rows when we talk about leading entries. Okay, this other matrix here, is this in reduced row echelon form? Well, here's the leading 1 for the first row, and indeed it's the only non-zero element in its column. So far so good. This is the leading entry for row 2, and it is the only non-zero entry in its column. Here we also have that's the leading 1 element for row 3, and notice everything above it is a 0 and everything below it is a 0. So these all check out. But then here is the leading 1 for row 4, and notice these 3 entries are not zeros. So this is not in reduced row echelon form. Okay. Notice this 4 and -4 here, that's okay. That's okay, because it's okay that those are there, because they're not in a column that contains a leading 1. So you only need to, it's only with the columns that contain a leading 1 that everything needs to be zeroed out, except for the leading 1. Okay, so so these two both check out. These are both in reduced row echelon form. Let me get rid of these. But because of these entries right here, this is not in reduced row echelon form. But it is in row echelon form. So we usually just shorten that to REF. Okay. The significance of row echelon form, we'll see, is that when your matrix is in row echelon form, you can solve the system at that point. You can just use back substitution to solve for all of the variables. Okay, we'll see examples of this. The significance of reduced row echelon form, if you're using an augmented matrix, then once you get the matrix into reduced row echelon form, you have well, if the system is, we'll see, if it's independent, then you can just read off the solution. If it's a dependent solution, then you have to take one more step to get a way to write down the solution. But basically, reduced row echelon form, your matrix is, you can just read off the solution, or you might have to do one more step, depending upon see on the next page. Okay, the Gaussian elimination method uses the three elementary row operations defined below to obtain the row echelon form or reduced row echelon form of an augmented matrix. The goal is to write the system in an equivalent form to be able to find its solutions quickly. Okay, now this is something you really need to memorize, what the elementary row operations are, because we will use these quite a bit. So 1, you can interchange any two rows. 2, you can multiply a row by a non-zero constant. And 3, you can add a multiple of one row to another row. So that's it. We have some little notation that we use to denote which row operation we're doing, so we can keep track of what we did. But the idea is, with Gaussian elimination, is you're going to take an augmented matrix, and then you're going to do a finite sequence of these elementary row operations until you get the matrix into reduced row echelon form, typically, or maybe just row echelon form. And then once you get it into reduced row echelon form, one of three things can happen. Okay, so let's see. So this talks about the existence and uniqueness of solutions. So given an augmented matrix for a system of linear equations, Gaussian elimination will yield one of the following three scenarios when the matrix is written in reduced row echelon form, this RREF. Okay, scenario 1 is inconsistent. This would be if the system has no solutions. The system will have no solutions if the RREF of the augmented matrix is of this form. Okay, and the key thing to notice here is this bottom row. Okay, the bottom row, remember, each row in a matrix corresponds to an equation, and the columns of the matrix, this is the, if we're using x, y, and z as our variables, the first column is typically the x column, then the y column, and then the z column, and then the augmentation column is the constants. But so what that row that I circled, what it corresponds to is, it corresponds to this equation: 0 times x plus 0 times y plus 0 times z equals 3. But if you just look at that equation, you'll see it has no solution. Okay, because no matter what you put in for x and y and z, when you calculate the result on the left-hand side, you're going to get 0. So 0 will never be equal to 3. So this is an inconsistent system. Okay, this corresponds, graphically speaking, when we have a 3 by 3 system, each equation in the system corresponds to a two-dimensional plane in three-dimensional space. Okay, the number of variables, x, y, and z, dictates the dimensionality of your space. Okay, and each equation, its graph will be one dimension less than the space you're in for each linear equation. So like in a two-dimensional space where you have x and y, each equation corresponds to a line, a one-dimensional subset of a two-dimensional space, the Cartesian plane. Whereas when your equations have x, y, and z, each equation corresponds to a plane, which is a two-dimensional surface or set in a three-dimensional space where you can go left, right, backwards, forwards, up, down, right? Okay, so geometrically speaking, if you have an inconsistent system, it means at least two of the planes are parallel and thus never intersect, and thus there's no solution. Because remember, what we're trying to do is find the set of all points that simultaneously satisfy all the equations in the system. If you have parallel planes, there's no solution. Okay, the next scenario is a consistent independent system. So the system has a unique solution if the reduced row echelon form of the augmented matrix is of the form, that you see here, where we have ones down the diagonal and zeros everywhere else. So only in this situation do you get a unique solution. Okay? And then the solution is, well, it's kind of nice because you can just read it off. It's just that column of numbers. The first one is the x. The second value is going to be for y. The third will be for z. And so we get this single point as our solution. Okay, next scenario. Remember, there's only these three possibilities that can occur for any linear system. No solution, a unique solution, or the third scenario, and that is infinitely many solutions. So in this case, we call the system consistent and dependent, and the system has infinite solutions if the RREF of the augmented matrix is of the form like we see here below. Okay, so if you get a row of all zeros in your matrix, and to keep things simple, we'll just always deal with square matrices here, or the coefficient matrix, when the coefficient matrix is square. When you get a situation like this, where you have all zeros in the coefficient matrix and you get a 0 in the constant column, then this is corresponds with the equation 0x plus 0y plus 0z equals 0. Well, notice that you could put in any values for x, y, and z, and it will work, okay? Because you're multiplying all of your variables by 0. So any value works, but hold your horses, because that's not the solution to the whole system, because we still do have the other two equations, and those other two equations, every single equation imposes constraints on the variables, or relationships between the variables that must be satisfied. Okay? But when we get one row of all zeros like this, and this is common, what we do is we say we have a free variable. Okay, one of the variables is free. And how do you determine which variable is free? Well, we have the x column, the y column, and the z column here. Now, this column contains a leading 1 coefficient, and so does the y column. But the z column does not contain a leading 1 coefficient in it, so z is free. Okay. So then what we do to write down the solution set to such a system is, well, we take the two remaining equations, and to this we add the equation z equals t. Okay, this is called parameterization, and the idea is that because z is a free variable, it means it can take on any value. Okay, any value, and we can still find values for x and y that will satisfy the other two remaining equations, no matter what value we give to z. So you could just keep using the variable z, but we often switch it to a single variable like t. And I'm going to do an example of this, and I'm going to go into the geometry of the solution set and all. But for right now, let's just all you need to think of is that what do? We take the parameterization variable, which in this case is z, and the constants, and we solve each equation so that the parameterization variable and the constants are all on the right hand side, and then the non-free variables are still on the left. Or I didn't say that right. Just all the variables are still on the left. Okay? And then we add to this equation the parameterization equation too, the z equals t. And so this is how we could represent the solutions to this system. In fact, what we could do is we could say that the solution is the set of all points of this form: 2 minus 3t, comma, negative 1 minus 2t, comma t, such that t is just any real number. Okay, and that would be the solution set to a consistent but dependent system. Okay, notice there's an infinite number of solutions here. You can pick any value for t and you get, and you can check this. This will satisfy all the previous two equations. Okay, it satisfies the entire system. Okay. Well, let's do an exercise here. Find the solution to the following system using Gaussian elimination to obtain the row echelon form of the augmented matrix. Then use substitution to solve for the remaining variable. Okay. So first step is to put this into an augmented matrix. So remember, we just need the coefficients 2, -3, 18, and then 5, 2, 7. Okay, and the goal here is this. We want to do a finite sequence of elementary row operations until we transform this matrix into this form 1 star 0 1 star star. Okay, where star is just any real number. Okay, any number. Okay, in other words, we want to put this into row echelon form where we have ones on the diagonal and zeros below, but we don't care about above the diagonal. Okay, so to do that, I'm going to rewrite the augmented matrix here. 2, -3, 18, 5, 2, 7. Okay, and let's see. I want to make this 5 here into a 0. So let's see here. What I could do is, well, unfortunately I don't have a nice situation where I have, you know, two opposite numbers, so I could eliminate very easily, but we can still make this work. Now you could like multiply the first equation by -5 halves and then add that to equation 3, row 2, but then we're going to introduce fractions into the coefficient matrix, and we really want to avoid introducing fractions if possible. So what I think I'm going to do is multiply row 2 by -2, or rather this. I'll just write it out. I'm going to do -5 times row 1 plus 2 times row 2. Okay? And the syntax I'm always going to use or the notation I'm going to always use when I write down my row operation is the row that comes second is always going to be the row that we're changing. So we're not changing row 1 here. We're just going to change row 2. Okay, and technically I'm combining 2 row operations into one here, but that's okay, because really you can only add a multiple of one row to another, right? But think of it like this. I'm multiplying row 2 by 2. That's a perfectly fine elementary row operation. And then I'm adding a multiple of -5 times row 1 to that new row. So here we go. -5 times row 1. I like to write it up above the row there. So -5 times row 1 gives me -10, +15, and -5 times 18 is going to be 50 plus 40 is going to be -90. Okay, 2 times row 2 is going to be 10, 4, 14. Okay, and then I'll come here and write the result of doing this row operation. Now remember, row 1 stays the same. It's 2, -3, 18. But row 2 changes and becomes 0 because we're going to be adding this to get row 2. We're going to get 0. 15 plus 4 is 19. And -90 plus 14, well, that's going to be 90 minus 10 is 80, minus another 4 is 76. So this will be -76. Okay, and let's see here. Okay, I'm going to do, I need to get, remember I have a 0 now here. Remember, this is my goal, this form over here. This is row echelon form. So I need to make this 2 into a 1, and I need to make this 19 into a 1. Okay? So my next row operation will be 1/2 times row 1. That's it. 1/2 times row 1 is going to give me, and this will introduce fractions, but it'll be okay because I'm almost done. So I have 1 here, -3/2, and 9. And then this stays the same, 0, 19, -76. Okay, and I'm going to now turn this element in the bottom right corner into a 1 by multiplying row 2 by 1/19. So I'm going to do 1/19 times row 2. And I do believe that 19 goes into 76 4 times because, yeah, 4 times 10 is 40, 4 times 9 is 36. Yeah, so we end up with 1, -3/2, 9, and then 0, 1, -4. Okay, and then this is row echelon form. Okay, we're almost done. So the second row corresponds with the equation 0x, because this is the x column, this is the y column. We only have 2 variables in a 2x2 system. 0x plus y equals -4. So y equals -4. Okay, now at this point I can substitute that value for y into the first equation. Okay, the first equation here is x minus 3/2 y equals 9. And I know what y is now, so I'm going to get the equation x minus 3/2 times -4 equals 9. Now I have an equation with one variable in it. I can solve that. I get, let's see, x plus 3 times 4 is 12. 12 divided by 2 is 6. So x plus 6 equals 9. So x equals 3. Okay, and we're done. Well, it might be nice to kind of write the solution set more formally as the point 3, -4. Okay, and there's our solution set. Okay, next exercise. Find the solution to the following system using Gaussian elimination to obtain the reduced row echelon form, RREF, of the augmented matrix. Okay, remember now the goal here is slightly different than the previous example. What we want to do is we want to do a finite sequence of elementary row operations until we have 1, 0, 0, and then any number, and then 0, 1, 0, some number, and 0, 0, 1, and some number. You know, this would be the case of it getting a unique solution. We may not get this. We may have a row of all zeros, or we may have an inconsistent system. We don't know yet ahead of time. In fact, it can be very difficult to tell until you do this elimination process, Gaussian elimination. Okay, so I'm going to write the augmented matrix over here, 3, 8, 6. Augment with 2, and then we have 1, 3. I'm just pulling the coefficients off of the variables, -2 and 1, and we have 1, 4, -2 and 2. Okay, so I don't have a 1 up in the top left corner. I could multiply the first equation, or sorry, first row, right, by 1/3, and then I would get a 1 there in the top left corner of my matrix. But if I do that, I'll introduce fractions, okay, because not everything there is a multiple of 3. Not every number in that row is. So instead, what I think I'll do is I'm going to swap or interchange rows 1 and rows 2, and that will give me a 1 up in the top left of my matrix because I need that. Okay, so I have 1, 3, -2, 1, and then now the first row becomes the second row. I have 3, 8, 6, 2, and the third row stays exactly as it was before, 1, 4, -2, 2. Okay. Now I'm going to start clearing out the elements below this pivot value. We call the ones on the diagonal, or any elements on the diagonal can be used as a pivot. A pivot is an element that you use to make zeros below or above that element. Okay, so I want to make this 3 into a 0, and I want to use that pivot. So the way I'm going to do it is I'm going to use, the pivot is in row 1, so I'm going to do -3 times row 1 and add that to row 2. Okay? Now I like to write down the multiplication here. -3 times 1 is -3. -3 times 3 is -9. -3 times -2 is +6. -3 times 1 is -3. So I'm multiplying row 1 by -3, and those are the values I get. Sorry. And I'm going to, let me erase that and that. Oops. I'm going to be adding that circled row to this circled row. Okay. And then I'll come down here and finish. So the first row stays the same, 1, 3, -2, 1. The second row changes though. I get a 0 here. -9 plus 8 is -1. 6 plus 6 is 12. -3 plus 2 is -1. But the third row stays the same, 1, 4, -2, 2. Okay. Now, my next goal is I want to clear out this 4, and I want to clear out this 1. Now, here's an important little point when doing this. The sequence in which I do these operations matters. Okay? I need to make sure that I've cleared out everything below my pivot before I start moving on to clearing out elements below the diagonal in the second column. Okay, so if I use this row above to clear out this 4, I'm going to be spinning my wheels. I won't be making progress on transforming this matrix into reduced row echelon form. Okay, so it's very important that I clear this 1 out first. And to clear this 1 out, I can use the pivot above it, that 1 that's circled. So I'm going to use row 1. I'm going to multiply row 1 by -1. So negative row 1 plus row 3. Remember, the second row is always the row that I'm going to be changing. So -1 times row 1 is -1, -3, +2, -1. I'm going to add that to row 3, to that row. And the new matrix I get, well, the first row stays the same, 1, 3, -2, 1, 0, -1, 12, -1, and then I have 0. Okay, now I'm adding the elements in the circled rows. -1 and 1 is 0. -3 and 4 is 1. 2 and -2 is 0. -1 and 2 is 1. Okay. Now, I could, at this point, column 1 is done. And now I want to move on to getting my column 2 to look like the column in the reduced row echelon form matrix over here up in the top right. Now, I could use this -1 to clear out the 1 below, but I could just swap rows as well. I think I'll do that. I'm going to swap rows 2 and row 3. I'll write my result from doing this in here. 1, 3, oops, that's -2, 1. Okay, now row 3 becomes row 2, so I have 0, 1, 0, and 1. Here I get 0, -1, 12, -1. Okay. Now I have a 1 on the diagonal. Okay, and I'm going to use this 1 on the diagonal. That's my pivot. I'm going to use it to clear out the entry below it, that -1. So how do I do that? Well, I'm going to use row 2. I don't need to multiply it by anything. I can just add rows 2 and 3. So I'm going to do row 2 plus row 3, and the result will go into row 3 because it's the second row in my sum there. Okay. So I'm going to be adding this row to this row, and the results will be 1, 3, -2, 1. This row stays the same, unchanged, 0, 1, 0, 1. Third row changes though. I get 0, 0, 0 plus 12 is 12, and then 1 plus -1 is 0. Okay. Now I'm very close. I almost have all 1s on the diagonal, and I do have 0s below the diagonal. So my next goal is to make this element into a 1. Oh, well, I can do this easily by multiplying 1/12 times row 3. Okay, so I have 1, 3, -2, 1, 0, 1, 0, 1, 0, 0, 1, 0. All right. Okay. Notice I already know, if you look at the last two rows, this is the x column, y column, z column. So this last row here corresponds to 0x plus 0y plus 1z equals 0. So z equals 0. I already know what z is now. Now the middle row corresponds to 0x plus 1y plus 0z equals 1. So y equals 1. I already know two of the variables, the values of two of them. But I'm not done yet here. I still actually have two row operations to do. But now that I've cleared out everything below the diagonal, now I want to start clearing out above the diagonal. But again, the order in which you do this does matter. You want to make sure you have everything in the rightmost column cleared out. If you have a pivot in that column, when we do here, we have a pivot right here. If you have a non-zero element on the diagonal, that's what I mean by having a pivot. If you have a non-zero element on the diagonal in that column, we can use it to clear out things above. So before I clear out this 3, in other words, I need to do this -2. Okay, so I'm going to use row 3. So I need to multiply row 3 by +2. So +2 times row 3, and then the destination row is row 1. I'm going to be putting that all into row 1, the result of doing that. Okay, let me erase this and that. Okay, 2 times row 3 is going to be 0, 0, 2, 0. And I'm going to add that to that. And I'm going to get 1, 3, 0, 1. Second row stays the same. 0, 1, 0, 1. Third row stays the same. 0, 0, 1, 0. Okay. Almost done. One more step. Notice, though, that this third column is finished, right? It has the leading one for the leading entry for this third row is a 1, and it's right here, and everything above it is cleared out. So we're making progress to reduced row echelon form. Now I go to the next column over, and I want to clear this 3 out and make that a 0. And what do I do to clear it out? Well, I use the pivot right below it. A pivot element always has to be an element on the diagonal. So what am I going to do? I'm going to change row 1, but I'm going to use row 2 to do it. So I'm going to do -3 times row 2 and add that into row 1. So -3 times row 2, that's going to be 0, -3, 0, -3. And I'm going to be adding that to that row. And I've run out of space here. What do I end up with? I end up with 1, 0, 0. Let's see, -3 plus 1 is going to be -2. And then everything else stays the same. 0, 1, 0, 1, and 0, 0, 1, 0. Okay, and now we're done. We can read off what x, y, and z are. X equals -2 from the first row. The second row tells us that y equals 1. The third row tells us z equals 0. So the solution set contains the single unique point -2, 1, comma, 0. Notice we started with a 3 by 3 system, meaning 3 variables. So every single point that is a solution to the system has to have 3 coordinates to it. And indeed, this does. Okay, now that we have a solution to the system, I want to use our calculator to check our answer. I want to show you how to do that. So let's pull up the calculator. And let's see here. Okay, so how do we check our answer? Well, there is a function on your calculator that will compute the reduced row echelon form of any matrix. So what we need to do is take the original augmented matrix of our system and store it in a variable, a matrix variable, and then compute the reduced row echelon form of that matrix. So the way to do this is you go into the matrix menu by hitting the second function key and then the x to the -1 key, and I want to edit a matrix, so I'm going to cursor over to the edit mode, and okay, it's already set up for a 3x4, but you could change these, like I could hit 2, enter, 3, enter. If I had a 2x3 matrix, doesn't matter. I'm going to cursor back up to the 2, change that back to a 3, enter, 4, enter, because we have a 3x4 augmented matrix. So now I just enter the numbers in. So we have 3, enter, 8, enter, 6, enter, 2, enter, and it takes me to the next row automatically, where I should put in 1, enter, 3, enter, -2, enter. Make sure you use the unary minus, and then 1, enter. Okay, and finally the third row is 1, 4, -2, 2. So 1, enter, 4, enter, -2, enter, 2, enter. Okay, we should just quickly check this. 3, 8, 6, 2, 1, 3, -2, 1, 1, 4, -2, 2. Looks good to me. All right. Okay, so now what I want to do is I want to go, I want to put a command into the command window. I want to put the RREF command into the command window. So I'm going to go to Matrix, and I need to cursor over to Math. And now I'm going to hit the up arrow key, and you'll see choice B is RREF, the RREF function. So I'm going to just cursor up to there, hit enter. Oh, that's not what I want. What this will do is it'll put that function into the first cell of that matrix. That's not what I want. So let's clear that. We want, let's just quit out of this. And now I go to the matrix. So you have to be in the command window before you pull the RREF command out of the catalog. So now we go to Math, up, 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 hit enter. And now I'm going to recall the name of the matrix that I want. So I go back to the matrix menu, and now I just want the name of the matrix. So I want matrix A, which is under 1, and then I close those parentheses off and I hit enter, and there we go. You see that that does agree with the reduced row echelon form that we computed by hand. So you can check your work with your calculator, and I recommend that you do that.